And you can know when you read it says express the height as a function of n. That means n goes first, h of n goes next. Okay, so okay, so 0 bounces. The ball hasn't bounced yet. No bounces yet. How high is the ball off the ground? The person who's going to drop the ball is standing on the balcony. How high is the ball? 10 meters, right? So the ball bounces once. After the first bounce, right? So the ball's up here, it drops. So this is the first bounce. How high is the height after the first bounce? It's 60% of this, right? So it's 6 meters, but I think we should say it's 10 times 0.6, right? Or we could say 0.60 if you wanted, okay? Then it drops and bounces again. Whoops, not that high though, right? It's going to get smaller and smaller each time. Now what's the height after the second bounce? It's 60%, well, I could say this is 6 meters. It's 60% of 6 meters, right? But I think the key to doing these questions is it would 10 times. If we show all the work, then you can see, and I think it's going to be 3.6 meters, right? If I show it in this way, can you see the patterning that's developing? Okay. After 3 bounces, what would it be? It would be 10 times 0.60, 0.60, 0.60, right? Agreed? So wouldn't it be more efficient to write it like this? Yeah? Okay, so what's the base? This is the base, right? The base is 0.60. Would you agree? That's the base, right? So if this is my function, this is sort of my x, and this is my y. If we want an expression for this experiment, I guess y equals 10 times the base raised to the exponent. So wouldn't it be h of n equals, the initial height was 10, this is my base, and that's my exponent, right, n? So the height of the ball at any given time would be equal to 10 times 0.60 raised to the power of n, because n is the number of bounces. All right, so that's the equation. Is this an increasing or a decreasing function? And why? Base is less than 1, right? So this graph should look like this, right? Which I think makes sense, because if I ask you to do a really quick thumbnail sketch, this is my h of n, which represents the height, right, in meters. And this is the number of bounces. Agreed? So at 0 bounces, how high was the ball? 10 meters?
Yeah.
After 1 bounce, how high was the ball?
0.6.
6 meters. And then after they actually dropped a bit more. Then it was 3.6, wasn't it, after the second bounce? So what's happening here? Decreasing, right?
Yes.
Perfect. Let's just keep going down. So everything's fitting with what we know. So after 8 bounces, you're just going to put that, I think part B actually asked for 8 bounces. So at 8 bounces, how would I represent that mathematically? H at 8, right, equals 10 times 0.60 to the exponent 8. That's why you need a calculator, right? Whoops. Handle. Okay, so how high do you think the ball's going to be? 0.17 meters. So h at 8 equals 0.17 meters. Now this is interesting, and maybe the science people can answer this for me, the physics people. When will the ball reach a height of 0 meters, according to our model? Okay, here's my equation. Oops, 10 times 0.60 to the n. When will my ball touch the x-axis? It never, right? This is my asymptote. So what does that mean? The ball will never stop bouncing, right? And I don't know, that's a physics question for you. You can come back to me tomorrow and tell me if that's true. Will the ball always hold some residual movement in it?
Yeah, probably.
Yeah, I think so, right?
Because of
It'll never ever stop. You can ask your physics teacher that one. Okay, according to our model, it'll never stop bouncing, right? It's always going to be, because if this is a real, like, I can always find 60%, like the value will never ever equal 0. There's nothing, no exponent I can put in there. All right, we're going to look at our logarithmic functions today. I started off yesterday with me telling you that the logarithmic function, let me see if I can do something different today. Sorry, other way. Just to see if I can get a little better for you guys. The logarithmic function is the inverse of the exponential function, right? And that's what I left off yesterday. I showed you that if we just took our critical points, and our critical points for the exponential function are 0 and 1, and 1 and the base, right? In this case, it's base 2. So if I take these 2 points, 0, 1, and 1, 2, and I just flip the coordinates around, I'll get 1, 0, and 2, 1, right? So there's my inverse points, and that gives me the inverse of the exponential function, which is called the logarithmic function. So this is how we write the logarithmic function. Y equals log, and we do a subscript, so it drops below the line a little 2, like the opposite of an exponent. Log in base 2 of x. So we can see that everything we knew about exponential functions are kind of just inverted for the logarithmic function. It's got its key points, we would say, are 1, 0, and whatever the base is, 1, right? And I'll go through that in a little more detail in our examples booklet. So we're just going to kind of look at the graph again, where the exponential function had a horizontal asymptote of y equals 0. The logarithmic function has a vertical asymptote where x equals 0, okay? So I just wanted to reintroduce that to you again. We're going to go to our examples booklet, and we're going to do, I've got some better examples to do here that we can actually excuse me. Here it is. Okay. So I'm on page 11. And once again, here we go. I think I'm going to go back to my old place, sorry. Do you have the booklet, Mohammed? Or Mohammed? I'll punch it later. Okay, so once again, exponential, logarithmic. We've done a base 3 graph because we had to have some base. So this is the graph y equals 3 to the x. This is log in base 3 of x. Here's my key points, and here's key points here. So you can see how they 0 and 1, 1 and 3. So this will be the point of 1, 0, and 3, 1. So let's see how they exactly mirror each other. The graph of 3 to the power x, we know this, it's just a graph with no shifting, so it's got a y-intercept of 1, horizontal asymptote of y equals 0, no x-intercept, domain of all real numbers, the range 0 to infinity, it's increasing. So let's see how it compares with the log of y equals log in base 3 of x. X-intercept of 1, right? Instead of a y-intercept, it has an x-intercept of 1, so that's a key point. The graph approaches the y-axis but never reaches it, so the vertical asymptote is x equals 0. No y-intercept, and the domain and range are flipped, right? The range now is all real numbers and the domain is 0 to infinity. This graph is also increasing though. That's the one thing they share. Everything else is flipped. Because if I read this graph from left to right, it's still traveling up, right? So let's just note this too. Let's do the key points of the logarithmic graph. Okay. So instead of 0, 1, it's going to be 1, 0, and whatever the base is, comma 1. And that's still, that little subscript is still called the base, right? We say log in base 3 or log in base 2. I'm going to get you, I wish I would have included. We're going to just flip over to lesson 6. We're just going to graph a couple of the log graphs, and then I'm going to come back to what a log function is. So let's just flip over here. Okay. I'm going to make you flip over to page 14. We're going to graph a couple of these. Okay, let's just, I guess I could just do that later, never mind. I'll erase that. All right, so graphing log functions, we just have to remember our key points and our key characteristics of the basic function. So we'll just graph it again here. This is just the log of x graph. So my key points are 1, 0, right? Instead of 0, 1, it's 1, 0. And then this will be the base, whatever the base is, comma 1. So I guess I should what's the base in this situation, by the way? Does anyone know? This is the interesting one about this. It's 10, right? For the first time, it's something unusual, right? Most times our invisible numbers are 0 or 1, but this one, this is called the common log it is base 10. So there's two logs that we use a lot in math and science. Base 10 log or base E, right? We were introduced to that number yesterday. So the 10 is usually never written. Just like when we never write coefficients of 1 or constants of 0. So when you see that there's no subscript, it's automatically base 10. Now, just as a point, this will become important when we start solving equations. When you look at your calculators and you see those two buttons, log and ln, your calculators can only do work with base 10s or base E. This is a base 10 log. So when I press the log button, and I put any number in here, or I'll do a different number. If I put log of 100, okay, it's automatically, it's a base 10 log. Your calculator's not going to show it. Okay, so that's, and when I use a ln button, Ln is just a shorthand for saying log in base e, okay? So log in base e of 1 is going to be equal to 0. And we'll talk about all that later. But your calculator can only handle base 10s and base e's, okay? So base 10 is a really important graph, so let's see. So that means the base is going to be 10, 1. Now there's no translations. Remember, a vertical asymptote will happen if there's a horizontal shift, but there's no shifting. So the equation of any asymptotes is going to stay as vertical asymptote, x equals 0. The domain should be 0 to infinity, right? And the range negative, positive, negative infinity, because there's no shifting for this graph. Okay. So I just have to figure out what the intercept is, and it looks like I've got it already, right? When y is 0, x is 1. So this one will have an x-intercept of 1, and the graph is increasing. All right, so let's plot these points. 1, 0. Maybe we should make everything go up by 2. 1 tick equals 2 units. Okay, so that means I'm going to have, my 1 is going to be between my first 2 tick marks, and then I'm going to have 2, 4, 6, 8, 10, and it's going to be up here, right? Because this is 2, 4, 6, 2, 4, 6. Okay, so 1, 0, 10, 1, and I'm going to sketch in my horizontal or my vertical asymptote. And connect the dots in a nice smooth curve and show that it's increasing too somehow. It's a very shallow increase, but that's it. So let's see, increasing, intercept of 1, vertical asymptote, domain is 0 to infinity, range is all real numbers, because this is increasing. It doesn't look like it, but it is. And that would be what the graph of a log looks like. Without any, if there are no shifts, if there's only stretches or compression and no shifting, your log graph is always going to take place in quadrants 1 and 4. Right? Exponentials take place in 1 and 2, logs 1 and 4. Okay, let's try this one. Y equals log in base 2 of x minus 1. What do you see here? What do your eyes see here? What's the base? Base is 2. That's important. Do you see any other transformations? One to the right. Okay. Does that shifting change anything? Does a shift right change anything? What does it change? Yeah, the new vertical asymptote then will be x equals 1, right? Okay, so maybe you want to sketch that in first. Let's sketch that in. All right, so let's write down our key points. So our key points would be, for a base 2 graph, it would be 1, 0, the base, 1. The only shifting was 1 to the right, so that affects my x value, right? I'm going to add 1 to x, y stays the same. So this will be a 2 and a 3, a 0 and a 1 stays. So let's plot those. 2, 0, and 1 tick equals 1 unit here. So 2, 0, and then 1, 2, 3, 1. All right, you have these 2 points and you have the asymptote. Does that give you enough to sketch? I think so, right? Increasing. There's an x-intercept of 2. What's the domain and range? Has the domain been changed? A shift will change the domain, right? So it's not 0 infinity anymore, it's 1 comma infinity. And the range is the same though, right? All real numbers? Okay. All right, let's try the next. Okay. All right, I want you to try the next graph for me, solo. This 1/2, the base is 1/2, right? That might change things a little bit, might change the shape of the graph a little bit, or the direction. I'm gonna give you a few minutes, because there's a few translations there for sure. A few transformations.
Just confused on that, yeah? Look at the power. Yeah.
Most people have made an attempt, which is great, right? I heard a couple people talking about x-intercepts, which is interesting and really good. Now, we did leave a space for intercepts, so let's see what you come up with here. So, there are lots of transformations on this graph, right? So my key points 1, 0, and then the base, which is a half, 1. Agreed? So what are my changes? What changes do you see here? Shift 1 left, so that creates x minus 1. Yeah, and then also this negative, right? Who does that affect, x or y? So minus y minus 2. All right. As soon as I see a shift, I've got a vertical asymptote. I know that affects my asymptote too, right? My vertical asymptote now is shifted 1 to the left, so it's going to be x equals negative 1. Agreed? Yeah. I always like putting that in because I tend to forget about those guys for some reason. So here's my vertical asymptote, and I've got it noted here. Okay, so let's do 1 minus 1 becomes 0, a half minus 1 becomes minus a half, and then I have 0 minus 2 is negative 2, negative 1 minus 2 is negative 3, okay? I guess I decided when I put my asymptote in 1 tick equals 1 unit. Okay, so 0, negative 2, excuse me, well there's my y-intercept, right? So let's record that y-intercept, negative 2, and then negative a half, negative 3, okay, so that's here. All right, do I know what's happening? Let's see. Looks like it's doing this, right?
Yeah.
Now, it sure looks like it's going to cross the x-axis, and it does. I just don't know where. And I don't know exactly how I'm going to find that. So let's just stop here for a sec. Let's fill in the rest of the info. So the domain will be from negative 1, right? Because that controls where my domain starts, the vertical asymptote, to infinity. The range is still all real numbers. And is this graph an increasing or decreasing? Increasing, right? Okay. Now, how do I find the x-intercept? Well, I'll tell you right now, we don't have the skills yet, kind of like the last time. But to find the x-intercept, what do? We sub 0 for y, right? And solve. So what we get is 0 equals minus log and base a half x plus 1 minus 2. So I'm going to bring my 2 over. And now I have this big mess, right? I guess I could divide out the negative, right? So if I divide the negative out, that'll be a negative 2. Okay, and this is where I've left off here. This is exactly where we're headed just this moment. After we leave graphing, we're going to figure out how we can convert this to figure out an x-intercept. And I know some people around here have prior knowledge, and they probably could do this, or I hope you could do this. So, anyone figure out what the x-intercept is? No? I thought someone in the crowd would get it. Okay, if I tell you this is your base, that's your log or the exponent, right? No? I think the x-intercept is 3. You want to trust me on that one? So if it's 3, that means it moves up like this. I guess I could have done that. Okay, let's just go with it that it's 3 right now. And I guess, could someone maybe program that into Desmos and see what it is? Let's see. Is it 3?
Yeah.
Yeah. Did you program it into your calculator?
No.
No? Okay. How do you know it's 3 then? You're just trusting me?
No. This one,
Let's see.
you cannot flip it over.
I'm gonna prove to you guys.
Half and flip it over.
Okay. Let's prove it. Minus log base 1/2. I don't know if this is going to work for me. X plus 1 is 2. No. Why can't I do, sorry guys, gotta figure out how to do a half, I might not be able to do it. I don't know where the log functions are. I can't find the logs on decimals here. Okay, well we'll leave it for now. Can't figure out how to do the base of a half. Okay, I'm gonna leave it now. I'm pretty sure, we know it crosses the x-axis. We'll come back to this graph. I'll just leave it like this. We'll come back to this graph and maybe you can even work it out on yourself, because we're gonna figure out today how to work with equations like these, right? And how exactly they're related. So I'm gonna put a big star here and I'm gonna come back to this and I'm gonna get you to figure out the x-intercept on your own. Let's do this last graph. Last one is important too, because it's the natural log graph. So I'm gonna put a little note here. Y equals ln of x is the natural log. Okay. When we had the last page over, remember when we started this whole graphing process? We had base, if there's no base given, it says log with no base, it's base 10. If you see the ln, and by the way, it's pronounced lawn, like your front lawn, okay? That means this is actually if we wanted to write it as a log, it would be log in base e of x. That's what that means. Okay, but you'll never see it in this form, but that means it's a log in base e. Because it's used so often, and to save time, they give its own symbol and it's called ln. But you know the base is e. All right, knowing that, that makes everything simple, I think. So what are my critical points? Like as long as you know what the base is, you know your critical points are going to be 1, 0, and e, 1, right? So everything else should fall into place now. So see, do a quick sketch of this one. And I would probably stick with 1 tick equals 1 unit. Okay, so hopefully your graph looks something like this, right? We have 2 points. I mean, there's no changes here, so it's just these points. 1, 0, and e, 1. And e is a number between 2 and 3, closer to 3, right? It's about 2.7. The function's increasing. The intercepts, we've got an x-intercept of 1, and we've got no y-intercept. What's wrong with me today? No y-intercept. Equations of asymptote, x equals 0. Domain, no change, 0 to infinity, no change from the base graph, and then the range is all real numbers. That's it. So if you see ln, that just means the base is e. If you see log with no base indicated, it means base is 10. And the reason those guys are so popular is like we live in a base 10 world, really, right? Every country except 3, I think, is metric, which means we use base 10 numbers. And the common log is, like I say, used for man-made measurements, right? Metric measurements, but the natural log is just a naturally occurring base. So many things grow in that base E, with that base E form. All right? I will give you guys a break, but we're stuck on this question, right? Like, how did I know, by doing a couple of little math twists and turns, how did I know that the x value here is 3? This is the base, this is the power, and this is the argument, it's called. So that's what we're going to talk, maybe I'll introduce that. We're going to go back a few pages now. And I'm going to show you how logs and exponents link together and how we can flip back and forth. When we get stuck in that log form, how you can flip out of the log form. I've already told you they're inverses of each other, right? So that means the equations themselves can be flipped back and forth. So I'll introduce that, and then you guys can go for a break. It says, converting between exponent and log form. Now, one thing I want you to know, the log, it becomes the exponent, right? The log and the exponent move back and forth, so the log itself is the exponent. Express each in logarithmic form. So 3 to the exponent 3 equals 27, correct? This is called exponential form. Obviously, right, we've got my base, the exponent, and the answer. If I wanted to write this in log form, this is how all the parts fit. I need that word log, okay? And that little subscript number is what we were calling the base, right? So what's the base here in this question? 3. That stays the same, okay? The answer to an exponential function goes here, okay? So what the answer to the exponential function is the argument, we call it. And the exponent is actually what we're looking for, right? The exponent is what we call the log. Yeah? So the log in base 3 of 27 is 3. So the log, if I say to you, find the log, I need to give you a base and an argument. If I'm asking for the log, I'm just asking for the exponent. So log and exponent are basically interchangeable. So log, what's the base here? The base is easy to see, right? The base doesn't change. The base is 4. What's the exponent in this question? The 0, right? So that's the guy that's separate, right? That's the guy, that's what you're looking for all the time. You're basically using logs to find exponents. So the exponent is going to be the answer. That's what you're looking for, right? So I would read this: log in base 4 of 1 equals 0. Because we're using logs to solve those tough exponential equations, so your answer will be the exponent. Okay, so log in base 5. I know my answer is going to be the -2 because that's the exponent. And this little piece is called the argument, just so you know. So this is the base. This is called the argument. And this is the exponent. So I can't say this enough. The only reason we study logs, it helps us to find those tough exponents, the ones we can't do with same base. All right, so let's keep going. Let's do these last 2. You do the last 3. Okay, so I got log in base 10 of 100 is 2. Log in base 2 of 1/16 is negative 4. Log in base 3 of 1/9 is negative 2. Agree? Once you get used to the code happening here, your eyes can kind of see, okay, that's my base, that's my exponent. Well, of course the answer is 100, right?
Can you rewrite that as just log 100 equals 2 if there's nothing in space time?
Where are we? Oh, this one? Yep. Or log of 100 equals 2. Perfect. Because it's the common log, right? Okay, I'm going to let you guys go for a quick break. Like between 5 and 10 after, we'll go on to the next one. And then we'll come back to that solving for the x-intercept. Or you could try that on your own. See if you can work the other way. Okay, and then I'm going to give you a little homework to do. And then I also have a hand-in assignment if you want.